Hello friends, welcome to this new video. In this video we discuss improper integral and convergence of improper integral when the bounds of the integrals are infinite. We define such a function as integration of f, here x is greater than equal to a. Then the convergence of this function is defined as limit a to infinity of f equal to limit capital X tends to infinity and integration of f. When the integral exists and the limit exists, the function is said to be convergence at plus infinity. Otherwise, it is said to be divergent. It is a very simple and important definition. We have to first evaluate the integral while taking x, capital X, instead of infinity, and then apply the limit x tends to infinity. If this limit exists, then we said the integral is convergent, otherwise it is said to be divergent. Similarly, we can define the convergence at negative infinity. Suppose my function is like this, integration of f, where the function have infinity at the left end minus infinity. Then we define this function as limit y tends to minus infinity y to b f into dx. So whenever here this x is less than equal to b, so whenever this limit exists, limit y tends to minus infinity, integration of f between the limit y to b, then this limit is said to be, the integration is said to be convergent, otherwise it is said to be divergent. Now friends, if we have both end at infinity, minus infinity and plus infinity, so we take a convenient point between minus infinity and plus infinity. Suppose that convenient point is a c. We distribute this limit into two parts, integration minus infinity to c and c to plus infinity. And in this equation number 1, when the first integrand is evaluated by using this definition, that means whenever minus infinity to c f into dx equal to limit y tends to minus infinity, integration y to c f into dx, and the second one is c to infinity f dx. This means limit x tends to infinity, integration c to x f into dx. If both these limit exist, then this integral is said to be convergent, otherwise it is said to be divergent. We can write it as in a single notation. Suppose minus infinity to plus infinity, this is a function. We take it as limit x tends to plus infinity, capital Y tends to minus infinity, and integration limits from capital Y to capital X f into dx. If the integral evaluated, and after if we apply the limit and limit exists, then if it is a converges, then if limit exists, then integral is said to be converges, otherwise it is said to be diverges. So these are the definitions of functions having infinity as a limit, in range is infinite. Now we see an examples. Suppose we would like to evaluate integration 0 to infinity sine of x into dx. Then We write it as limit capital X tends to infinity and 0 to capital X sin x into dx equal to limit capital X tends to infinity. Integration of sine is minus cos x between the limit 0 to capital X equal to limit capital X tends to infinity minus cos of capital X minus minus plus cos of 0. Cos of 0 is 1. So this limit is converted into capital X tends to infinity 1 minus cos of capital X, and cos of capital X as x tends to infinity not exist, therefore the limit of this function is not exist. Hence this function has no the improper integral does not exist. We write here the improper integral does not exist, does not exist. Now let us take one more example. Suppose I would like to integrate minus infinity to plus infinity dx divided by 1 plus x square. Then this will be limit capital X tends to plus infinity, capital Y tends to minus infinity, and from capital Y to capital X dx divided by 1 plus x square. Now 1 divided by 1 plus x square, the integral is limit capital X tends to plus infinity, capital Y tends to minus infinity, tan inverse of x, and between the limit capital Y to capital X. Limit capital X tends to plus infinity, capital Y tends to minus infinity, tan inverse of capital X minus tan inverse of capital Y. At plus infinity, this is a tan, this is pi by 2, and at minus infinity we have minus pi by 2. Minus minus plus pi by 2, so this is 2 into pi by 2, and we have limit is pi. Limit exists and therefore the improper integral is convergent integral. Another example, integration of 2x square divided by x raised to 4 minus 1 between the limit 2 to infinity. Upper bound is infinite, hence we take it as limit capital X tends to infinity and 2 to capital X 2x square divided by x raised to 4 minus 1. 2x square divided by x raised to 4 minus 1, this will be 2x square divided by x square minus 1 and x square plus 1. In terms of partial fraction, this is ax plus b divided by x square minus 1 plus cx plus d divided by x square minus 1. Hence we get 2x square equal to ax plus b into x square minus 1 plus cx plus d into x square minus 1 x square plus 1, so this will be plus, and here we have minus 1. Then a into x cube plus a into x plus bx square plus b plus cx cube minus cx plus dx square minus d, or a plus c into x cube plus b plus d into x square plus a minus c into x plus b minus d. Then you can see that we have equations a plus c equal to 0 and a minus c equal to 0. That is, here we get a equal to 0 and c equal to 0. Another equation is b minus d equal to 0 and b plus d equal to 2. If you compare the coefficient of like coefficient of x, like coefficient x square coefficient, and here in the side right side the x square coefficient is b plus d. Then from this b equal to d, as b equal to d we have 2b equal to 2 and b is equal to 1. Therefore b equal to d equal to 1, and this term 2x square divided by x raised to 4 minus 1, this becomes 1 divided by x square minus 1 plus 1 divided by x square plus 1. Okay. Now again we can write this x square minus 1 as 1 divided by x minus 1 into x plus 1 plus 1 divided by x square plus 1. For example, here again apply the partial fraction. 1 divided by x minus 1 into x plus 1 equal to a divided by x minus 1 plus b divided by x plus 1 equal to a into x plus 1 plus b into x minus 1. Now we get new equation. 1 is equal to a into x plus 1 plus b into x minus 1. Let us put x is equal to 1. If we put x is equal to 1, we get a equal to 1 by 2. Again if we put x is equal to minus 1, we get b is equal to minus 1 by 2. Hence, the total term is converted into integrable terms. Integrable terms that will be, that is 2x square divided by x raised to 4 minus 1. This becomes 1 by 2 divided by x minus 1 plus minus 1 by 2 divided by x plus 1 plus 1 divided by x square plus 1. Now we can integrate this. Integration of the first term, then integration of this is equal to integration of 2x square divided by x raised to 4 minus 1 into dx is equal to 1 by 2 into integration of this is log of x minus 1 minus 1 by 2 log of x plus 1, and integration of this is tan inverse of x. 1 by 2, if we take 1 by 2 common, log a log minus log b log of x minus 1 divided by x plus 1 plus tan inverse of x. Hence limit x tends to infinity, integration 2 to x 2x square divided by x raised to 4 minus 1 equal to limit x tends to infinity tan inverse of x plus 1 by 2 log of x minus 1 x plus 1 between the limit 2 to capital X equal to limit capital X tends to infinity, apply the upper limit tan inverse of x plus 1 by 2 log of capital X minus 1 capital X plus 1 minus tan inverse of 2 minus 1 by 2 into log of 2 minus 1 divided by 2 plus 1. Then the first term, if we apply the limit tan inverse of infinity, we know that tan inverse of infinity is pi by 2, so this will be pi by 2, and here you can see that this will be approximately 1, and hence log of 1 is 0, therefore we have 0 minus tan inverse of 2 and minus log of 1 divided by 3. So pi divided by 2 minus tan inverse of 2 minus log of 1 by 2, here 1 by 2 1 by 2. This is the limit of this integration, improper integration, and it is finite. Okay. Now let us evaluate the integration of x cube into e raised to minus x square into dx between the limit 0 to infinity. Again, limit capital X tends to infinity, 0 to capital X, x cube into e raised to minus x square into dx. Friend, here we put x square equal to t. If we put x square equal to t, 2x into dx equal to dt. Hence, integration x cube into e raised to minus x square into dx. This becomes integration of x cube, that means x square into x. So x into dx is 1 divided by 2 into dt, and x square, we have distributed this x cube into x square. So x into dx is dt, and this x square, for this x square we write t e raised to minus t, okay, into dt, right? Then 1 by 2 into integration, we apply the product rule. First function t e raised to minus t divided by minus 1 minus e raised to minus t divided by minus 1 into integration of t is derivative of t is 1 into dt, okay, equal to 1 divided by 2 minus t into e raised to minus t, minus minus become plus, integration of e raised to minus t is again e raised to minus t divided by minus 1. Now we can take minus common, there is minus, here is minus, so minus 1 by 2 into t into e raised to minus t plus e raised to minus t, or minus 1 by 2 t plus 1 e raised to minus t. Then integration 0 to infinity x cube into e raised to minus x square into dx equal to limit capital X tends to infinity. So we have evaluated this minus 1 by 2, t means x square plus 1 e raised to minus x square between the limit 0 to capital X, minus 1 by 2 into limit capital X tends to infinity, upper limit capital X square plus 1 into e raised to minus capital X square, minus lower limit at 0 plus 1 into e raised to 0 equal to, here at infinity, x square divided by e raised to minus x square, e raised to you can see that x square is greater than this x square, right? Therefore the limit, you can see that this is greater, and hence this goes faster than x square. Therefore x square divided by e raised to x square, this term, this is greater, and hence this goes faster to infinity than the numerator. As denominator goes faster, this tends to 0. So minus 1 by 2 into this term will be 0 at infinity, and hence we have now minus 1. Minus minus become plus, and we get 1 by 2. So this improper limit will be now 1 by 2. So in this manner we can evaluate the improper integrals when the range of the integration is infinity.